All right. Okay. So let me see about that. Okay. But let's get started with the class, and then I'll send an announcement on Blackboard about Thursday's class. All right. So let's see where we are. So again, what we have been doing in the last class was basically, we're trying to formulate these rules. Okay. Ultimately, what we are trying to do is to respond to a client, to respond to a problem specification, right? And trying to design a system. So the first thing, so I would always go in this sequence when we're trying to do this. Okay. So you're given a problem description, and oftentimes that's the one that is coming from the client. That's the one that is, that you have been asked to design. And what does the client say, really? The client wants you to design a system that he'll give you the constraints, he will give you what the system should be doing, okay? And you will gather the information, right? And you would basically put this in a more organized fashion, okay? So what you will be doing this is basically you will synthesize the information, and from that information you look at what are the inputs that are going into your system, going in, right? How many inputs are there? So these are some of the questions that you should be asking. How many inputs are there? Now this approach is a generic approach. It's not just for the design of digital systems. It could be design of any engineering system. Okay, so this design approach is very generic. Okay, so in this case, of course, for this class, when we talk about inputs, these inputs correspond to binary inputs, right? Inputs that can only take 0 or 1 value. Okay, now so you look at how many inputs, and likewise, what are the outputs expected? And how many outputs are there? Okay, so these are the questions that you should be coming up with. You don't have to come up with the solution right away. Okay, you're not looking at the solution right away. You're trying to do this in a more organized fashion. Okay, step by step. And if you're able to follow this through, then if you can actually get through these 2 steps, which are the most fundamental steps, you're almost halfway through the problem. Okay, so now you can basically put the information down, which we call that the level 0 diagram, where you will show what these inputs are. How many inputs are there? You have already determined how many inputs there are, so you'll basically show those inputs. Okay, this is what you want to design. That's something that you want to design. And let's say these are some of the outputs coming out. So you've determined these in the first step in the level 0 diagram. How the problem is done once you're able to decipher that, because once you do that, you're almost there. Now the next step is to see how the outputs are dependent on the inputs, how the outputs are related to the inputs. Now, specifically in the design of combinational circuits, that's pretty simple, right? It's as simple as saying, okay, this question basically translates to your truth table, right? The truth table that would give you the entire snapshot of your system, okay, for all different combinations of the inputs. What should you be expecting for the outputs? So that's your truth table, really. So once you're through these 2 steps, then your 90% of the problem is done. The 90% of the design problem is basically taken care of. The rest of the steps are basically more or less manually intensive steps. You really don't have to think much in those steps. The thinking process really happens in this stage. Once you're through this stage, when you're trying to actually implement the circuit itself, that's more or less, very, very mechanical, I would say. You don't have to really use your brain there much, because you just have to follow the protocols, follow the rules that we have seen in the last class, and you're done. Okay. All right. So let's. So that's the approach that I would suggest you to take in the design of any system. Okay. Okay, Julia, do you have anything? So this is a problem description. Yeah, that's the problem description. That's correct. Yeah. So the problem description comes from the client or somebody, or from me, for example, when I'm like in terms of asking you to design a system that corresponds to some certain operation. That's the problem description. Okay. Now let's. So in the last class, we went from the truth table, right? Now once you're given the truth table, how do I obtain the simplified function? Again, we want to go for the simplified function, right? Because again, what we have discussed, based on what we have discussed, we want to have the simplified function because we want to make it compact, we want to make it faster, power efficient, and so on and so forth. Right? So we're always going for simplified function. And when I say simplified function, that means the function that has fewer number of gates to be used. Not just the number of gates, but also the inputs going to the gate. Okay. All right. Because more the number of gates, more power consumption, more larger your circuit becomes, more complex your circuit becomes, and so on. The truth table, what are the different steps? In the last class, we introduced the concept of minterms. Okay. Minterms, which are your product terms between the inputs. And we can express the function as a sum of minterms. Right? And when we express the function as a sum of minterms, we call that the canonical sum of products expression. Okay? And we would use the Boolean identities to simplify the canonical sum of products expression. Now, what is the most important identity that we'll be using most of the time, right? Now, basically, we'll be using this identity. If I have, for example, A, B, C prime plus A, B, C, okay? Now, every time I see some expression like this, I have two product terms. Going from one product term to the next product term, I only have one variable that changes. In this case, C prime to C, right? That means I can basically take out the other product term, the unchanging product terms as a common factor. In this case, combine the changing product terms, right? Very similar to your arithmetic algebra that you're familiar with. You can take it as a common factor, and then that's the ones that are changing, so that cannot be obviously taken as a common factor. So now C plus C prime, we'll use identity here. Any variable or, because the plus operation is nothing but the OR operation, or with itself basically is 1, right? C plus C prime or X plus X prime is always 1. So that goes to 1. So that's basically leaves me with A and B as a simplified term, right? So from going from canonical sum of products expression, I'll be using this identity most of the time to simplify my function. Okay, and this is exactly what we have done in the last class. We have also discussed the concept of max terms. Okay, now max terms are the sum terms between the inputs. These are the sum terms between the inputs. I can express my function f as the product of max terms. Now, how do I express this? Again, I choose those max terms for which my function is false, and then basically express them as a product of max terms. Okay. And again, the logic behind why we want to choose those max terms for which the function is false, we have seen this in the last class, right? So I hope you still remember that. Okay. Again, for the minterms, I would express the function as a sum of minterms by choosing those minterms for which my function is true. Okay. So that's how you express the canonical sum of products. That's how you obtain the canonical product of sums expression. Okay, that's your canonical product of sums expression. Now, when I'm trying to simplify functions, canonical product of sums expressions, most of the time I'll be using these identities. Okay, so let's say I have x plus y, very similar to what we have done here, x plus y prime. Now I'll be using the identity where the distributive law essentially, okay, for the OR operator. So I can basically express this as x plus y prime. The way we have done the identity, we basically went the backward way. We started out with this. We distributed the plus operator to obtain this expression, right? So of course, the alternate is also true. So if I see an expression like this, x plus y times x plus y prime, I can express this as x or y prime. Okay. Now, if you observe, going from this sum term to this sum term, I have one variable that changes, y changing from y to y prime, right? So these are the common terms that I take out, and then the one variable that changes, I basically express this as y prime. Now, any variable that is ANDed with the complement of itself will always be a 0, right? Because if y is 0, y is 0, obviously that goes to 0. If y is 1, y prime is 0, that goes to 0 as well. So that goes to 0, and I would end up with x. Okay. All right. So you start with the truth table. I would express the function either as a product of sums expression or a sum of products expression, the canonical sum of products expression. And then I will be using my Boolean identities. Most of the time, these are the ones that we'll be using to simplify my function, to combine terms and eliminate variables from my expressions. Okay. All right. And in the last class, we have done this. We have looked at one example for the canonical sum of products expression, going from there and simplifying it to get this simplified sum of products expression. And let's now finish the max terms expression. Okay. Now the max term, the same function, the truth table of last week, the max term expression that we got was something like this: f equals. Let me see if I have that written down. So that was A plus B plus C times A plus B plus C prime times A plus B prime plus C prime. Okay, and now we will use the identity again, going back to that. Every time I see something like this, x plus y prime, I would express this as x plus y prime. That gives me x. I will use that identity, the distributive law, to simplify this product of sums expression. Okay. So what do I have? Now, the trick is you observe these sum terms carefully, going from one sum term to the next sum term. Every time I only have one variable that changes, I would combine them. And I see that in this, when I go from here to here, my A and B are constants, they don't change. Only one variable changes, C changing from C to C prime. So I can combine them using this identity, where my x in this case will be A plus B because they are not changing. I'll write this as A plus B plus C prime. Okay, and of course you still have that, which is A plus B prime plus C prime. Now C prime goes to 0, so I end up with A plus B and A plus B prime plus C prime. Now, would that be the most simplified function? Can I simplify it further? Is that the most simplified function? What do I do? Any suggestions from the class? Can I simplify it further?
Can we distribute A and B?
Distribute A and B. I can do that. We could do that. So you want to basically, yes, we can do that. And you should do it and see what you get. BB prime plus C prime. A plus BB prime plus C prime. It can just be A. Okay. All right. So let's do that. So I can, because in this case, I have A common. I can probably write this as A plus B times B prime plus C prime. Do that, right? Using the same distributive law, I can probably write that. In which case, I get A plus BB prime plus BC prime. Again, BB prime goes to 0. I end up with A plus BC prime. Again, this is something that we started out with. So that's good. So you got the same expression. Okay. Another way, again, is I can still use this identity x times x times x, any number of times, it's still x. Right? We have seen that in the last class. Any variable ANDed with itself, any number of times, would provide you with the same answer. In other words, if I see this, A plus B plus C prime, if I look at these two expressions in the original problem, even in this case, I could have combined these two, right? Because A is common, C prime is common, only one variable changes, B to B prime. In other words, I can reuse this one again without changing the value of the function. I can reuse this term. Again, this again, remember that this is an alternate approach. I'm just trying to, illustrate. So if I did that, what do I get? So I have A plus B plus C prime. If I did that, so this is one approach. Here, what do I get? I will have A plus B from this combination, from A plus B from this, A plus B from this combination, and then from this combination, what do I get? I have A, which is common to these two, C prime, which is common to these two, and then BB prime, right? Because that's the one that changes. Then BB prime, that goes to 0, and basically I get A plus B or A plus C prime. You can still function. You can still simplify that using again the same distributive law. I get basically A plus B C prime. I could have stopped here, in which case I would call this as the simplified. That's the simplified product of sums expression. Right? This is a product. This is the product of sums expression. That's the simplified product of sums expression. So if you're asked to express the simplified function as a simplified product of sums expression, then you should your function, your answer should be in this format. Okay, something to remember. All right. Any questions here until this point? Does that make sense? You can use multiple different identities here. Most of the time, we are going to use few identities. Yes, Julia.
So for the first approach,
Mm-hmm.
you're saying that we could use the one you're pointing at as the simplified.
Yeah, this again, so the first approach is correct. There's nothing wrong about that. The only thing is the answer that I get here is in the form of the simplified sum of products expression, right? Sum of products expression. If you're, let's say in the exam, you're asked to, without really explicitly mentioning, I ask you to simplify the function into the simplest form without explicitly mentioning if it should be in the form of product of sums or sum of products, then you're free to choose any approach, and then you get, the simplified expression. On the other hand, if I ask you a simplified product of sums form, then I would expect your answer to be in this product of sums form. That makes sense? Of course, you
Yes.
can always do this even after getting this, right? BC prime. I can always express this by using the identity as A plus B times A plus C prime, right? Going from here to here, distributing the plus operator between B and C prime. I get the product of sums expression. So either way, so whatever method you choose, you need to conform to the question. As long as you're doing that, then that's fine. As long as you understand that, then that's fine. Does that make sense?
Yes. Thank you.
Okay, very good. Okay. What else? Any other questions on this before we move on? So we have looked at how to come up from a canonical sum of products to the simplified sum of products. We also looked at how to go from a canonical product of sums to the simplified product of sums expressions using Boolean identities. Okay. All right. So that's good. If you don't have any other questions, now there is another way of doing simplification, much more faster and much more easily, okay, than using Boolean identities. Now you may have seen, right, in some of the in the last class and this class, when you're trying to use Boolean identities and trying to simplify a large function, it may not be obvious to you where to stop. Where do I stop? How do I know that the function that I got is the most simplified function? Can I go further? Am I missing any identities? Right? So these are some of the questions that may easily crop up. Now, to address those, we have another approach that would, if you follow the exact rules, that would always give you the simplified function, no matter what. And it's more quicker. Okay, so that way it's kind of our lifesaver. And we call that the Karnaugh map approach. Or in short, I can just call this K-map approach. Okay. So again, you will see that there is not much difference in the way this map approach works. We are still using the identities, the Boolean identities, but in a more systematic manner. That's all it is. Okay. And the K-map itself, you will see that it's nothing but the truth table. Really, what we try to do there is going from the truth table, we are trying to express the truth table in a much more compact fashion. Okay, that's all we're doing. All right. Now, so what is it? So what is that K-map approach? How does it work? Okay. Now, let's go back to the same example. So we have ABC, and that's the function that we were trying to. So that the truth table consisted of all of these, combinations between the inputs. And then the output was, again, we're going back to the same function this time. So this was the function that we started out with, right? And trying to implement that using the Boolean identities way. And now we would like to implement that using a new approach called the K-map approach. Okay. Now, what is the K-map? It consists of basically cells. Okay, cells. this table or this K map is basically consisting of the cells, and the number of cells in the map is equal to the number of minterms. Because each cell is really holding a minterm. Now, when I'm looking at a 3-input function, I have 8 minterms, right? I have 8 input combinations. That means I have 8 minterms, because each input combination will have its own unique minterm. So I have 8 minterms. So if I want to draw a K-map corresponding to this function, which has 3 inputs, then I would have 8 minterms, 8 cells associated with that. So I will first draw a map that contains 8 cells. I have 1, 2, 3, 4, and that's 8, right? And let me call this A, let me call this B, C. It's very similar to your matrix, right? Now, A can take values 0 or 1, so I'll place that. All right, that's 0 and 1. A changes, or the values that A can take is basically 0 and 1. B and C can take values between, so I look at the all possible combinations between B and C. Okay, so these numbers correspond to the value that are being taken by B and C. These numbers correspond to the values taken by A. Okay, so now in effect, I have 8 cells, 8 different combinations of the inputs. Now, each cell, as I mentioned before, holds a minterm, right? Now, what is the minterm corresponding to this cell? The number is, again, you can write the number of this, the minterm number is 0, which is basically A, B, C of 0, 0, 0. The binary value of that is 0, so that's the minterm number, 0. And the minterm corresponding to this combination, 0, 0, 0, going back to the last class, was A prime, B prime, C prime, right? All right. Now, the minterm number corresponding to this cell would be again 0, 0, 1. That will be 1. And the minterm corresponding to this cell would be A prime, right? 0, 0, 1, B prime, C. And likewise, I will look at
001 is 0, right?
0, 0, 1 is 1, right? 0, 0, 1. That's M0, M1. Oh, okay. I know what you're saying. You're talking about the function. You mean this function? Okay. Yeah. Now these numbers are not representative of these functions. These numbers are corresponds to the minterm numbers. Okay, minterm positions. So the numbers I'm writing here, basically they correspond to the minterm position. I have not described the function yet. I'm just looking at the cells, the description of the cells, and so on. And I will get to that in a few minutes. So in this case, that will be A prime, B, C prime, A prime, B, C, A, B prime, C prime, A, B prime, C, A, B, C prime, A, B, C. And the numbers again, so that's 0, 1, 0 is 2, 0, 1, 1 is 3, 1, 0, 0 is 4, 1, 0, 1 is 5, 6, and 7. So I have 8 cells. Each cell holds a minterm, and the minterms themselves are these, corresponding to these combinations of the inputs. So that's your K-map. Okay. All right. Now let me define the rule of adjacency. The rule of adjacency. What that means is two cells in this K-map are said to be adjacent if going from one cell to the next cell, I only have one variable that changes. Okay, two cells are said to be adjacent if going from one cell to the next, only one variable change happens. One variable changes. Okay. Now, let's take this example of between 0 and 1, the minterms or the cells 0 and 1. Okay. Are they adjacent according to this rule? Of course, they are. They are touching each other. They're next to each other. They're physically adjacent. We can already see that. But are they adjacent according to this new rule? Here I have A prime, B prime, C prime, the minterm, A prime, B prime, C. And I can see that only one variable changes. When I go from this cell to the next cell, only one variable changes. Which one? C. C changing from C prime to C. Right? The rest of them do not change. A prime, B prime remains constant here between these two cells. A prime, B prime is the common factor. Only one cell changes. So these two cells, so in this case, in this example, 0, cell number 0, cell number 1 are adjacent according to the definition. What about cell number 0, cell number 4? Are they adjacent? They are adjacent, right? Because B prime, C prime are the common factors. They don't change. Going from here to here, A changes. Only one variable changes. They're adjacent. Very good. What about these two cells? Are they adjacent? 4 and 5? A is common. B prime is common. C changes. 4 and 5 are adjacent. Only one variable changes. They're adjacent. What about 1 and 2? Are they adjacent? Now between 1 and 2, they're not adjacent, right? Even though they're sitting next to each other, they're physically adjacent. But according to this definition, they are not adjacent because when I go from here to here, A prime is fine. That's constant, doesn't change between those two cells. However, B changes from B prime to B. That's one change. C also changes from C to C prime. Two changes. So these two cells, even though they are present next to each other, they are not adjacent according to this rule of adjacency. Okay. Now, so what we need to do is we want to make sure that we draw a K-map where the cells that are physically adjacent are also adjacent according to this rule. So what we will do is the simplest thing that we can do to ensure that that happens is we switch these two positions, okay? These two positions. So instead of specifying it as 1, 0 and 1, 1, I will do 1, 1 and 1, 0. When I do this, of course, the minterms corresponding to these two cells, these four cells also get switched. And now they physically adjust. So doing the change, that switch here, changes these numbers as well, of course. Those minterm positions change. Okay. So what do I have now? What is the minterm corresponding to this cell? Well, let me say what is the number corresponding to this cell? That will be 0, 1, 1, which is 3, 0, 1, 0, that is 2. The number corresponding to this cell is 1, 1, 1, which is 7, 1, 1, 0, which is 6. So of course the cell's position changes, the minterm positions changes, so the numbers change, and the minterms themselves changes. So the minterm corresponding to this cell now would be A prime BC, right? A prime BC. The minterm corresponding to this cell will be A prime B, C prime. A prime, B, C prime. Minterm corresponding to this cell now becomes A, B, C. And this cell would be A, B, C prime. Okay. Now, by doing that change, doing that flip, I have ensured that all the physically adjacent cells, I'm not talking about the diagonal cells. I'm not talking about these cells. I don't care about those cells. But the ones that are physically next to each other, like these, they share a common side. They're adjacent, right? Whether it's this side or this side, doesn't matter. Whether it's the vertical edge or the horizontal edge, as long as they're sharing an edge, they're adjacent. Okay, the way I've written them down here. Adjacent according to the rule of adjacency, not just according to sitting next to each other. Now we can see between this cell and this cell. Are they adjacent now? A prime, C. So I have two variables that do not change. So that really leaves me with one variable that changes, B, B prime, and B. So these two cells are adjacent now. What about 3 and 2? Again, A prime B is common. C changes, so only one variable changes. So these two cells are also adjacent. And likewise, you will see that these two cells are adjacent, these two cells are adjacent, these two cells are adjacent. So the physically adjacent cells that share a common side now becomes adjacent according to this rule of adjacency by changing that, by making that flip. Okay. All right. So that's good. So again, this K-map essentially represents the truth table in a more compact fashion. This truth table can be expressed in a much more compact form using this K-map. All right. Now, what is the next step? Okay. So now you understand what the K-map is, what is composed of. Okay. So this is how I would draw for a 3-input K-map, 8 cells. For a 4-input K-map, I would have 16 cells because I would have 16 minterms, 16 different input combinations. I would have 16 cells for my K-map. All right. Now, once I have this, again, every time I draw the K-map, I don't have to mention the individual minterms. Okay. So my K-map would basically, this is more for description, but now that we know what these cells contain, what the minterms associated with these cells are, I don't have to, show them anymore. If you really want to know what those are, you can simply read them from these values, right? From the values of the inputs for each cell, corresponding to each cell. Right? In this case, again, I don't have to explicitly show that. The minterm corresponding to this cell will be A prime, B prime, C prime. Right? And likewise for the other cells. All right. Now, the next step, once I draw the K-map, once I number these minterms, positions for each cell, okay, it's just a matter of expressing the truth table in the K-map format. For example, the truth table corresponding to this function would be what? You basically place ones for those input combinations for which the function is true, right? The function is true for 0, 1, 0 combination, 0, 1, 0 combination, that's a 1. I place a 1 there because that's how my function looks. My function is true for 1, 0, 0 combination or the minterm number 4. Okay, let me write those minterm positions as well. Okay, so from 4 through 7, the minterm positions 4 through 7, my function is true. So the K-map corresponding to this function would be decided by these ones, the position of these ones within the cells. So this K-map that I drawn here and this table are basically equivalent to each other. This is much more compact than the table. Okay. So then that's the next step. The first step is, of course, you draw the K-map, the right format. Okay, so that the physically adjacent cells are next to each other, or are adjacent to according to the rule of adjacency. And then I fill in the ones for which my function is true. Fill in the ones in those cells or in those minterm positions for which my function is true. Okay, that's what I have here. All right. Now, before we actually start executing the simplification process, okay, let me describe what this K-map actually does. What really happens in this approach? As I mentioned before, let's take a simpler example. We'll come back to this later. For now, let's actually examine what's happening. Okay. Let's say I have, two cells. In this case, I place ones in those two cells. Let's say my function is something like this, just two ones in these minterm positions. Again, empty cells indicates that they are filled with zeros. I don't have to really explicitly show that, but you can show that, which is also fine, but I don't really have to show that, right? Okay. So what really happens now? When I have these cells, when I have these ones within the cells, or when I have these adjacent cells containing ones, let me put it that way. When I have two adjacent cells or containing ones, I can combine them into a combination like this, something like this. Okay. Now, again, when I combine them, and every time I combine them, every combination produces a product term. Every combination of adjacent ones or adjacent cells containing ones produces a product term. And how do I write this product term? Okay. The technique to write the product term is simple. So what you do is you go from one cell to the next cell. You keep those variables that do not change and eliminate the variable that changes. So that's the rule. Okay. From this cell to this cell, what are the variables that do not change? Again, remember that these cells are actually containing minterms. Okay. Now going from this cell to this cell, okay, A remains as A prime because the minterm corresponding to this cell contains A prime. So A remains as A prime. Going from this cell to this cell, B remains as B prime. Again, the minterm corresponding to these two cells contain B prime. So B remains as B prime. C gets eliminated because C is changing from C prime to C. So I preserve the ones that do not change, eliminate the ones that do change. So in this case, the variables that do not change correspond to A prime and B prime. So the product term I'm going to get from this combination is going to be A prime and B prime. So in other words, I don't have to do any algebra here anymore. I don't have to apply any identities anymore. I can simply write down the product term directly just by looking at what are the variables that are changing when I go from one cell to the next, and what are the variables that do not change when I go from one cell to the next. That's all it is. Okay. So again, I can do that only for adjacent cells. A cell, let's say I have two cells here. These two cells are not adjacent, right? So I cannot combine them into a single combination. I can only combine adjacent cells. All right. Okay. Now, how does it work? Again, this is no magic here, really. It's what we're really doing is applying the Boolean identities again, right, in a more faster way. If I had to write down the expressions, what do I get here? What are we doing here? The minterm corresponding to this combination would have been A prime, B prime, C prime. And I'm combining this with this minterm, which is A prime, B prime C. And what do you get? So I have A prime B prime as a common factor, C plus C prime, or C prime plus C, right? That goes to 1, and I get A prime B prime. So you're basically doing this, you're basically applying the same Boolean identities in the K-map, but in a more systematic, faster way, without explicitly doing the simplification, doing this algebraic expression and trying to do the simplification. You can directly write down the product terms. Okay. Now, okay, so that's good. Now let's say instead of just 2 adjacent cells, now what happens when I have 4 adjacent cells like this? So this cell is adjacent to this cell, this cell is adjacent to this cell, this cell is adjacent to this cell, and this cell is adjacent to this cell. Okay, I have 4 adjacent cells. Okay, I can combine them into a single combination. So as long as they're adjacent, I can combine them into a single combination. I will use the same rules. Every combination of adjacent cells containing ones will produce a product term. And how do I get this? I keep those variables that do not change when I go from one cell to the next. Eliminate the variables that do change. Okay, so what are the variables in this 4-cell combination? How do I do this? I go from this cell to this cell. What changes and what do not change? From this cell to this cell, I see that my B remains as B prime, does not change. So that's there, that's part of the product term. Okay. When I go from this cell to this cell, right, my A changes. A changes from 0 to 1, so that's eliminated. So when I go from this cell to this cell, my C changes, right? So basically my product term basically consists of P prime, a single variable P prime. So the product term that corresponds to this 4-cell combination would be basically B prime, and that's it. How do I get this? Again, we are basically applying the Boolean identities, right? What you have here is A prime, B prime, C prime, A prime, B prime, C. Here I have A, B prime, C prime, A, B prime, C. Now, if I were to do the algebraic simplification, I would combine these two. Combining these two would produce me A prime, B prime. Combining these two would produce me again. I'm sorry, I should not. Let me not do this. Okay. Combining these two cells would produce me A B prime. Right. Now combining these two produces me B prime. So instead of doing this multiple steps, you can simply combine the 4 adjacent cells and just eliminate the ones that do not changes. Keep the ones that do not change. Okay. All right. As simple as that. So now, as you can see, we need to, when we're trying to combine them into a larger common, so your goal is to combine adjacent cells into the largest possible combination. Okay, making sure that your combinations are always in terms of 2 power n combinations. You can combine one cell, n equal to 0 corresponds to one cell. So basically, you may have a K-map where your cell cannot be combined with another cell. Okay, so that's a combination of one cell. N equals 1 corresponds to 2 cells. I can combine 2 cells, 2 adjacent cells. N equals 2 corresponds to 4 adjacent cells. I can combine 4 adjacent cells like we did here. I cannot combine 6 cells because we lose the symmetry when I do the 6 cell combination. Or I cannot combine 3 cells, 3 adjacent cells. For example, if I have 1, 1, 1, I cannot combine them into a single combination like this. Because if I combine these two, I get something, and then I won't be able to combine that with another cell. So you lose the symmetry here. But here, when it's in terms of 2 power n combinations, I'll have that symmetry, like we have seen here, and can reduce that into a simpler term. And likewise, so n equals 3 corresponds to 8 cells, 8 adjacent cells combination, and so on. So your combination should always be in terms of 2 power n to preserve that symmetry, to preserve when you're trying to combine and eliminate, it should always be in terms of 2 power n. Okay. All right. So our goal, if I want to get the simplest term, simplest expression, would be to combine the adjacent cells to the largest possible combination. For example, in this case, combining these 4 adjacent cells as 2 and 2 adjacent cells, that would not give me the largest possible, that's not the largest possible combination of adjacent cells, right? And in effect, that will not produce me the simplest expression, because if I were to do that, what do I get? I would get 2 product terms corresponding to each of these combinations. So the product term corresponding to that would be what? That would be A prime. A doesn't change when I go from here to here, and then C gets eliminated, so that's A prime, B prime. The product term that I get from this combination will be, again, A, B prime would be here. C gets eliminated when I go from here to here. That will be A, B prime. And my function f would read as A prime, B prime plus A, B prime. Now, is it the simplest function? Can I simplify it further? Did it give me the simplest form? And the answer is no, right? Because I can see that my B prime is a common factor. I can still simplify it. So obviously did not give me the simplest form. If I do not combine into the largest combination of adjacent cells, I will not be getting the simplest function. Here we had more scope for simplification just because I did not choose the largest combination. I basically choose 2 individual combination of 2 adjacent cells. Okay. That will be B prime. That's correct. All right. So these are the rules that I'm going to summarize them again. But do you have any questions until this point on what are the K-maps, what the cells represent, what is the approach, what does the combination means, how do we combine them, and how do I write the product terms corresponding to each combination? Any questions before we move forward? And as you can see, if you do this right, if I make sure that my combinations are the largest possible combinations, you would always end up with the simplest form. No questions about that. Okay, if you don't have any questions, so let me just summarize what we have done, and then we'll take some examples now. So the K-map approach, K-map is nothing but the truth table in a more compact form. First, you draw the K-map. With the number of cells equal to number of input combinations or I can also say the number of minterms. Both are identical, both are same. Okay. Make sure that the cells are adjacent. Make sure that the physically adjacent cells, that means adjacent cells are adjacent according to the rule of adjacency. Okay, then you place ones in the cells for which the function is true, or for which the given function is true. That means the cells that do not contain anything is assumed to be containing zeros, right? All right. Fourth, then you combine the adjacent ones. Combine adjacent cells, cells containing ones to the largest combination, to the largest possible combination. And we have seen why we want to do that. Okay. And then finally, each combination produces a product term. Gives a product term. And how do you obtain the product term? You go from one adjacent cell to the next adjacent cell, both horizontally and vertically. You eliminate the variables that change. Keep the variables that do not change. Okay. So each combination gives a product term, and you know how to get the product term. And finally, your function f is a sum of all these product terms. So that's the mechanism that you would apply in obtaining the simplest functions through the K-map approach. Okay, so now let's get back to the original problem and let's see if you are getting the right answer. Okay. All right, so the original problem was again we had 3 inputs. That means I have 8 minterms. I would have to draw the minterm, my function f BC. I can express this as sigma m. What was that? Let me see what the function was. Okay, so that's 2,
4, 5, 7.
That's correct. Thank you. I can write this in terms of minterms as 2, 4, 5, 6, 7, right? And now I can draw the K-map corresponding to that function. It's my A, B, C, 0, 0, 0, 1, 1, 1, 1, 0, 0, and 1. Okay. That's 2. Okay, let me write down the numbers. 0, 1, 2, 3, 4, 5, 6, 7. So those are the minterm positions. I'll write down, place the ones in the cells containing those minterms. In this case, that will be 1 here, 1, 1, 1, 1. And now I need to combine the cells. I see that this cell is adjacent, these two cells are adjacent, these two cells are adjacent, these two cells are adjacent. That means I can combine these 4 adjacent cells into a single combination. Okay. I also see that this cell is adjacent to this cell. I can reuse this cell and combine this, because every time I combine them into a larger combination, I'll be able to get a more simplified function. So I would, if I need to, I can reuse the cells that are already being combined. Like for example, this cell has already been combined with this cell. I can still reuse that with this adjacent cell. Okay. So I have 2 combinations. Each combination would be producing a product term. Okay. Let me call that 1. Let me call that 2. Okay. And let me write down what the product terms are. So what is 1? Again, going from this adjacent cell to this adjacent cell, I'll keep those variables that do not change. The variables that do not change when I'm going from this cell to this cell are B and C. B existing as B, C existing as C prime, right? In these 2 cells. A gets eliminated. A changes from 0 to 1. So A is eliminated. The ones that do not change when I go from here to here are B and C prime. Okay. What is the combination 2? Again, I eliminate all the variables that change, keep the variables that do not change. So as you can see here, A doesn't change. A is 1 across all these combinations. A remains as 1. That means A. From here to here, C changes. C gets eliminated. From here to here, B changes. B gets eliminated. So when I go from here to, when I go through these adjacent cells, I see that B and C are changing. So B and C gets eliminated. And I end up with what that doesn't change, which is A. Right? What is my function then? My function is basically a combination of these 2 product terms, 1 and 2, which basically gives me A plus BC prime. No need for algebra. I can just read out the product terms directly, just looking at what are changing, what doesn't change when I go from one adjacent cell to the next adjacent cell in a combination, and keeping the ones that do not change and obtaining the product term. Okay. As simple as that. Okay. So you will see that this K-map approach, once you get some practice, once you start actually doing some problems, this will be like a second nature for you. You'll be easily be able to start doing this. So after some time, it will actually become more of a mechanical thing for you. There's nothing to really think here. Once you get the technique, it's basically a technique. Once you get it down, it's just a matter of doing it the right way, and you'll get it. The most important thing is, or the most important place where you really have to think is the first few steps, coming from the problem description and going to the identifying the inputs, outputs, putting down in the level 0 diagram and the K-map. Okay. Once you're through that, everything else pretty just falls in place. Okay. Any questions here? Okay.
Real quick. What if 4 is 0?
What is 4 is 0? Okay. That's a good point. Let's see what happens. How do I combine in that sense, in that case? So let's say this is 0. Okay, let me draw that. I have something like this. So that's 0, 1, 2, 3, 4, 5, 6, 7. I have 1 and 1 here. 4 is 0, so I won't put anything there, let's say. And I have something like this. How do I combine them now? Again, according to the rules, I cannot combine 3 adjacent cells together. 3 cells together. So I cannot have a combination of 3 adjacent cells. I lose the symmetry. Again, these 2 I can combine. Okay. and I can combine these two, right? I cannot combine 3, so I can basically combine these two. I have 2 product terms. Again, that corresponds to B, C prime, because A gets eliminated. When I go from this to this, what do I get for this product term? I have A doesn't change as A, and then from here to here, based on these values, I can see that B changes from B prime to B. C remains as C, so that's AC. So my function for this case would be AC plus BC prime, and that's the simplest function.
Okay, so we can combine 7 and 6 then.
You can combine 7 to 6 also. Again, and what you're going to get is another product term. That's a good point. And I'm going to talk about that in more detail in the next class. But what happens is you'll get a product term. What is the product term when I combine 7 and 6? That will be AB, right? Now my function now reads AC plus BC prime plus AB. Now, if I did not combine them, because these two cells are already accounted for, this one is accounted for in this combination, this one is accounted for in this combination. So even if I did not combine them, I'm getting the function. This function would work. It would not, and just merely adding this other term does not change the value of the function. The function would still work, but I'm increasing the complexity unnecessarily. Whether you add it or not, it's not going to change how the function would behave. Does it make sense?
Okay.
So that becomes a redundant term that's there, that's really not contributing to the function at all. I mean, it's not changing the value of the function at all. If this and this produces the same output, then what's the point of having this additional term?
Okay.
Because the important thing is you have to account for all the ones in the K-map. In any combination, when I combine the adjacent ones, I need to make sure that each of my 1 is accounted for, at least in one combination. As long as that is satisfied, I'll get the right function. In this case, I'm accounting that this one in this combination, this one in this combination. So I have already accounted for all the ones. Okay. So it's not necessary to do this combination of 6 and 7. That's correct. So it's not really necessary here. And in the next class, we'll actually define them in more formal ways. What these combinations are called. We have a more formal name associated with that. And that will clarify this a bit more in the next class. Okay. But the important thing is we need to account for all the ones in at least one combination. So if there is another one here, let's say, then I have not accounted for that, then that means whatever function I'm getting is not going to be the function I want. And now I have to make sure that I account for this one as well somewhere. Let's say I have a 1 here. Now, can I combine this? Do I see any adjacent cells here?
Yes, number 2.
That's correct. Even though I don't have any physically adjacent cells containing 1s, but if you notice this cell and this cell, they are adjacent according to the definition, right? Because when I go from this cell to this cell, I have 0, 0, 0, 0, 1, 0. My A doesn't change, A remains as A prime. When I go from here to here, B changes because B is changing from B prime to B. C remains as C prime, C. So I can combine this cell, this with the number 2 in this way. So I can account for that one in this combination. Okay. Then let me call that 3. And what would that be? What is the product term corresponding to 3? Now, A doesn't change, so A prime remains.
And C prime.
And C prime, right? C prime. That's it. Okay. So yes, another important thing is those cells need not be adjacent, physically adjacent to each other to satisfy the rule of adjacency. And in this example, we can already see that this cell and this cell are not physically adjacent, but they still satisfy the rule of adjacency. So they're still adjacent to each other. Okay. All right. In the next class, we will talk about, we will look at more examples with 4 input K-maps, okay, in which case we'll have 16 cells. We'll talk in more detail about what are these combinations called, and what are these combinations called, and what are these, what we just described, is there a special name associated with that, redundant combinations, okay? And there is certain rules, again, for those, what we can use and what we should not use, and how do we actually, eliminate the redundant terms, and so on, okay? And we'll do that in the next class. And I will pause here and let me see if you have any other questions on the K-maps. Okay, so if not, then I'll see you guys on Thursday for now, okay? And you guys have a good rest of the week.